Good afternoon, biology. Today we're going to talk through the second half of chapter 9, which is respiration. Looks like I have my build feature on my PowerPoint, so bear with me here as I get all the info on each slide for you. All right, so we'll start off with glycolysis. I used to read this intro from our textbook to kids to introduce this topic. I'll just kind of paraphrase it for you. So the intro went something like this. It talked about how energy is stored in foods, and they specifically talked about grains. And if you have ever heard or saw in the news about like a grain elevator starting on fire, it's kind of a common, I wouldn't say it's super common, but it happens quite a bit where elevators will have a fire or even explode, and grain dust can be very, very touchy. Basically, it can build up, and if it's not cleaned up, it can actually start on fire or cause explosions. So this particular picture here is actually from Devil's Lake. This is a elevator that my dad owned in his business, and there was a buildup of some dust in some location, they believe, and it started on fire. So this was in it was like a January or February night, I believe. And this was, of course, them putting it out. And then the next morning, maybe it was January. Either way, it was winter. And all the ice built up there and the remnants of the building. Pretty crazy. So I threw those in there. I took those off the Herald site after that happened. Thank goodness for insurance, right? All right, so we'll start off talking about glycolysis today. And this is the first step in cell respiration. Okay. Now, I know the crash course video went into quite some detail. We're going to simplify these things. And so this really is the extent of what I want you to understand. So glycolysis, the word itself means sugar breaking. And so if you look at the word here, glyco, okay, if you recall glucose, all right, so it's referring to glucose here, and lysis usually means in biology to break apart, okay, break apart or separate or divide, okay, and so here what we have is we're taking a sugar, we're breaking it down, okay, so we're breaking down one molecule of glucose, and notice here the 1, 2, 3, 4, 5, 6, okay, the 6 glucose C6H12O6, right? So these 6 black spheres here are referring to the carbon atoms, okay? And we're breaking it down. So we see it go from 6 down to 3 and 3, all right? So we're splitting it in half, basically, make it into a smaller molecule. And what that is called is pyruvic acid, okay? And so we see pyruvic acid down here. Oops, I'm going to hide this. There we go. And in the process, we also get some ATP, all right? In reality, we actually have to use some ATP to do this. So we use 2, we end up creating 4. So if you spend $2 and you get $4 back, you've made $2, right? Same idea. So overall, we're getting 2 ATP made, okay? And this takes place in the cytoplasm. So really, that's all you need to understand. I'm not going to require you to draw all this out here or anything. I just want you to know, what do we start with? Okay, we start with glucose in this. We're breaking it down into a simpler thing called pyruvic acid. And notice that pyruvic acid is pushed on to the next part, the Krebs cycle. Okay. And some of these high energy electrons are pushed towards the electron transport chain. So we're getting some things done that helps drive the next couple of processes. All right. And remember, 2 ATP made. So energy molecules are getting 2, and this is taking place not in the mitochondria, but in the cytoplasm. All right, we'll go on to the Krebs cycle here, and might as well get this taken care of right now. No, you do not have to memorize the Krebs cycle. I probably was supposed to memorize it in college, and I can't tell you that I was very successful at that. That was not a strong point for me. So no, we're not going to make you identify or label or draw any part of this. All I want you to know is from this diagram, it's a cycle. Okay, so what that means is, notice here at the very top we have glycolysis. So we're taking the pyruvic acid, or pyruvate is another name for it, taking this from glycolysis and starting this cycle. Okay, and it's a cycle because it's just a loop. Okay, once it goes through, we keep going. All right. I did have a student one time memorize the Krebs cycle because I told him he didn't have to, and he thought he better do it. He was very successful at it. Unfortunately, the rest of the test didn't go so well for him. So he had a great diagram of the Krebs cycle he drew on the back page just to show me he could do it. And that was all he was able to do. So you got to pick your you only have so much time in a day, so make sure you pick properly what you're going to try to learn. Okay, so this was named after a guy called Hans Krebs. We take the pyruvic acid from glycolysis. We're going to further break that down, and we're going to get some energized electrons. Okay, so just remember there's these electrons that come from this cycle that are going to be used later. We make another 2 ATP with this cycle. So once again, we're getting some energy out of it. Not a ton, but some. And we're also making carbon dioxide. So when you guys breathe out your carbon dioxide, it's due to this Krebs cycle, as you saw in the crash course video. And this does take place in the mitochondria. All right, we move on to the last step, the electron transport chain. And my goodness, look at the picture. There's a lot going on there. I'm not going to, require you to draw this out or anything like that. Let's just know the basics. Okay, so this takes place in the mitochondria. In fact, across the inner membrane of the mitochondria. And this uses products from the 2 previous steps, glycolysis and the Krebs, and those high energy electrons. And this is where we get the biggest bang for our buck. Okay, this last part of respiration, this is where we get 32 ATP. And I know in the video, the crash course guy might have said 34, if I remember right. So there is a discrepancy there. This is based off our textbook, so I'm going to stick with it because that's our main source for class. But either way, it's a lot more than 2, right? So if we add those all together, 2 from glycolysis, 2 from the Krebs, and 32, we get 36, right? And I think Crash Course said 38, but either way, it's a good number, right? So we have glycolysis, Krebs, and the electron transport chain. We get 36 molecules of ATP for every molecule of glucose. Okay, so for every molecule of glucose we ingest and break down, 36 molecules of ATP. What does that mean? Okay, let's take a look here. So your cells don't only use glucose. I want you to understand that. We focus on that because it helps us to explain these processes, but you can also break down lipids, proteins, and carbs for energy, right? I mean, if you think about it, we always reference carbs in this scenario when we talk about food and energy. Okay, breads and pastas, and we know that we get a lot from that. So your cells are basically like a furnace that could really burn anything. Okay, The furnace in my house hooked up to natural gas, which most of yours probably is. If you live in an older house, maybe it's oil. If you live in a really, really old or simplistic house, maybe you burn wood or coal, right? Like a fireplace. So your cells are basically a furnace that can do anything. It's kind of like the DeLorean time machine on Back to the Future 2 when he's pouring in the garbage and stuff to make it work, right? Doc Brown and Marty McFly. So that seems like it's pretty good, right? So how efficient are we as cells? Maybe not as efficient as you'd believe, okay? Even though our cells can burn nearly everything, 36% efficient. So where does the rest go? 64% of that energy is released as heat, okay? Like after you work out, helping just to keep your body temp regulated, keep all your organs functioning properly. And so the energy that we generate through these processes, 64% of it we can't really use in our body is released as heat. So how does that compare to like a car? Actually, better than a car. So even your car engine, you pour gasoline in there, fill it up, and drive around. Your car, I'm not sure of the exact numerical value, but it is less than 36% efficient. So I know that seems really low. You know, if you were 36% efficient in biology, you'd have a failing grade, right? So kind of interesting. And also very interesting that we haven't been able to make a car that can match what our cells can do. That's pretty cool. All right, let's touch on fermentation here. So fermentation, remember cell respiration was talking about using oxygen, right? An aerobic process. But if we don't have oxygen, okay, let's say the cell isn't able to have a supply of oxygen to use, we can still create ATP. We can still get energy made through fermentation. Okay, and there's two kinds. So we'll touch on those two kinds here. First is called alcoholic fermentation. Let me get my pictures and stuff here. Okay, this is the one that you saw in the previous lesson on fermentation in the video and through the website. This is what is how wine is made, and those other drinks. But it's also what causes bread to rise. So if you've ever if you've ever baked bread, you maybe you knew this. Okay, so alcoholic fermentation produces two things. It produces ethyl alcohol. What did I do there? There we go. And carbon dioxide. Okay. Now, when you look at bread, we know that if we eat this bread, we don't become intoxicated, right? The alcohol, when you bake the bread, burns off because alcohol has a really low boiling point, and so it vaporizes rather quickly. So we don't have any alcohol in that bread. However, we do have these spaces, okay? And these spaces, if you ever wondered what these pockets are in your bread, that's where the carbon dioxide forms and it creates a bubble inside. And then when you end up slicing your bread, there's a space. Okay. So if you've ever bought a loaf of bread at the store and opened it up and there's a giant hole through like a bunch of the pieces, you always feel like you got ripped off. That's just how it goes. Okay. We can't control where those CO2 bubbles form. So, all right. The other kind of fermentation is called lactic acid fermentation. And this you may have heard of before, particularly if you've been in like a sport or something that requires workouts and advice from coaches. They may have talked about lactic acid. So let's show you what this is all about. Okay, whole bunch of info there. That's actually a picture of me in college. One of the few pictures that were that I got actually from college. This is from college cross country, I believe. The national meet in Wisconsin, I think. And no, I'm not winning. um, I was probably somewhere in the middle of the pack there. Okay. Anyway, lactic acid fermentation produces lactic acid. Certain bacteria can do this. And this is the type of fermentation that gives us foods like cheese, yogurt, sour cream, pickles, and sauerkraut. So I know some of those probably at your age are foods you like, such as cheese and maybe yogurt. Sauerkraut and stuff, it has to grow on you a little bit. So but your muscle cells produce ATP by this. It's called lactic acid formation. Okay, so if you've ever done an exercise like some sprinting, something really anaerobic and really like powerful, and your legs hurt, your muscles were just like sore and they felt like rocks, and that's because of the lactic acid that is built up in your muscles. Okay. So we can kind of look at, what kind of exercise could you be doing? Okay. Are you doing a quick burst? Are you doing a 50-meter sprint? Are you doing skating lines in hockey, crushers in basketball? For those quick bursts, the ATP in the muscles that's already stored there, as well as ATP that is made by lactic acid fermentation, because we don't have time for that oxygen to become part of that. Okay. If you're doing something for more than about a minute and a half, okay, like here running a cross country race or a marathon, or you're biking or something for a long way, then of course, we do have to breathe, right? You're breathing in. You can't hold your breath and do that like you could if you were lifting something heavy. So if it's an activity that's more than about 90 seconds, then cellular respiration is the best. Okay. And so we tap into those processes. So just showing different ways your body can tap into ways to basically do what it needs to do. And that is the end of chapter 9. So thank you for watching, and we'll see you later.